In number 3, we are asked to find all the discontinuities of this function x squared minus 4x divided by the quantity 55x squared minus x. And we are asked to label the discontinuities as removable or non-removable. All right, so to find the discontinuities, what we need to do is set the denominator equal to 0 and solve. Right, this is a rational function which consists of a polynomial divided by another polynomial. So I'm going to go ahead and factor the numerator and the denominator. Each has a common factor of x. Now we set the denominator equal to 0, and then we set each factor equal to 0. And so this gives us the solution x equals 0, and this gives us the solution x equals 1 divided by 55. So those are two discontinuities. Now we just need to decide whether each one is removable or non-removable. Well, we go back to this form of our function, our original function, and that simplifies to x minus 4 over 55x minus 1. You might remember we said that if this factor could be canceled, that's going to give us a removable discontinuity, and if it cannot be canceled, then it's going to give us a non-removable one. In 4a, we are asked to determine which values of a will make this piecewise defined function continuous for all values of x. Alright, so this function is defined in two different ways. To the right of 2, it's defined to be ax plus 1. That is a polynomial. It's a linear function, depending on what the value of a is. To the left of 2, and at 2, it's defined to be x squared. That's a polynomial. My point is that the two pieces are continuous where they're defined. It's just a matter of determining whether the two pieces line up. So what we need to do is find the limit as x approaches 2 from the right of f of x, and the limit as x approaches 2 from the left of f of x. So what we need is for the limit from the right and from the left to match in order for this limit to exist. So the limit from the right is going to depend on the ax plus 1. And so that's going to be a times 2 plus 1. Right? A is a constant. So when x gets really close to 2, this is going to get really close to a times 2 plus 1, 2a plus 1. Okay. What about from the left? When x is less than 2, we're dealing with this part of the function, and let's see, as x gets close to 2, x squared is going to get close to 4. These two need to be equal in order for the function to be continuous at 2. We know it's going to be continuous everywhere else. It's just at 2 that that is an issue. So we will set these two things equal, and we get 3 equals 2a, or a equals 3 halves. So for when a is 3 halves, this piece and this piece will line up. The graphs of those two parts of the function will line up, and we'll have continuity everywhere. So in this problem, we're going to look at, we need to decide which value of a will make this function continuous for all values of x. So this is a piecewise defined function, and each piece is defined by a polynomial. And so each piece is continuous everywhere. In fact, we've got two lines. One has a slope of one has a slope of 3, and the other has a slope of 5. They are not parallel, so they do cross. So they might look something kind of like this. So what we've got to do is decide on A, which is the transition value, where the function switches from one definition to the other. And so what we want to do is choose that transition value so that the resulting function and its graph are both continuous. So I hope it makes sense that what we really want to do is choose this intersection point for A, because then it'll come up, the graph will come up along this graph, this line, and then it'll go off on that line. If we put the A on either side of that intersection point, we'll have a break in the graph and the function will not be continuous everywhere. Alright, so what we're going to do then is just set these equal, these two expressions, and we'll solve the resulting equation, and that should give us the x value of the intersection. So I'm going to add 1 to each side and subtract 3x from each side, and that should give me 8 equals 2x divided by 2, and we get x equals 4. And so that's the value of A that we want. A equals 4. In number 5, we have a limit proof. So what we've got to do is evaluate the limit as x tends to 3 of 5x plus 2, and then prove that that is the actual value. Alright, so the limit of 5x plus 2 as x approaches 3 is going to be, I think that's 17. And I made a mistake down here, which I will correct. So what we've got to do is prove that that is actually the limit of that function at that point. So what we've got to do is show that this definition holds. For every positive number epsilon, there is a positive number delta, such that whenever x is such that the absolute value of x and of the difference of x and c is between 0 and delta, then we have that the absolute value of f of x minus L is less than epsilon. So this can be thought of as the distance between x and c, and this can be thought of as the distance between f of x and L. F of x is also y. So what this is really saying is that by choosing x close enough to c in this case is 3, we can make y sufficiently close to L. L is 17. Alright, so let's see how this works. I'm going to start this off with some scratch work, and then we will turn that scratch work into a proof. Alright, so we actually work backwards. We start from here and then work our way up to that. Okay, so we need to start with the absolute value of f of x minus L is less than epsilon. Well, how's that going to work? Well, f of x is 5x plus 2. The L is 17. And so let's see, we need to simplify this. That would be the absolute value of 5x minus 15, I think. Now, we can take out a common factor of 5. And this is good, because what we need is the absolute value of x minus c. C is 3. That's what we need. So we divide each side by 5. And so we have finished with the scratch work. What we've got to do is, for any imaginable epsilon, we have to find a delta that, quote, works, unquote. Well, this is how you find the delta. You let delta be epsilon over 5. Then if x is within this distance of 3, f of x, or y, will be within epsilon of 17. So if we make x that close to 3, y will be that close to 17. Alright, so let's turn this into a proof. How are we going to do that? Well, basically what we're going to do is we're going to take this and turn it around backwards and then throw in enough explanation that the whole thing flows smoothly. So we start with the limit, we'll start with the statement. Prove that the limit as x approaches 3 of 5x plus 2 equals 17. All right, so here's the proof. Let epsilon be positive and arbitrary. We don't get to choose the epsilon. The epsilon could be anything as long as it's positive. So that's why I'm saying it's arbitrary. It's unspecified. We are making the stipulation that it be positive, but otherwise we couldn't get very far. So let epsilon be positive and arbitrary. Further, let delta equal epsilon over 5. If you need a refresher on how all this works, there is a video in the chapter 1 videos that explains what's going on here with these limits and these epsilons and deltas. Okay, so now we start out by this way. Let x be such that 0 is less than the absolute value of x minus c. C is 3. And the absolute value also needs to be less than delta. So right now, all the proofs at this stage are going to look almost exactly the same. The only difference is this expression and what number goes in there. This number is that number. Okay. Now what I'm going to do is do some substitutions and some manipulations that will end us up at the correct point. So remember back to our scratch work. We are basically at this stage. I've got the epsilon over 5 written as a delta, and I don't have the 0 here, but otherwise this is what I have. What we're going to do is trace this backwards until we get to this stage. Okay, so what follows from this? Well, I'm going to drop the stipulation that this be greater than 0 because we don't really need it for the rest of this proof. All right, since delta is equal to epsilon over 5, I can make that substitution. Now, if we multiply each side of this inequality by 5, we get 5 times the absolute value of x minus 3 is less than epsilon. That's that line right there. Now we just need to go back up to here and then up to here, and we will essentially be done. Okay. So distributing the 5 yields the absolute value of 5x minus 15 is less than epsilon. Which can be rewritten as the absolute value of 5x plus 2 minus 17 is less than epsilon. And that's what we needed to show. Right, we needed to get back to right there. And that's where we are. We're done. We can indicate the end of the proof with a little box like that, or you could use a symbol that looks like that, sort of 3 slashes, or you could just use the old standby QED. Any of those 3 will work. Putting in all 3 seems to be a bit much.